the stage is yours.
Okay, well, thanks. It's so much fun to be able to do this. It's well, I love talking to undergrads and trying to give an idea. I think it's really important for any scientist of any sort, and certainly a theoretical physicist, to try and explain what it is we do, because we so often devolve into technicalities. That's a good thing. Technicalities are essential, to making progress. We've got, one of the great things about physics is we've got centuries of people ahead of us doing all these marvelous things, and we build on it. This is one of the spectacular things about physics. And so, of course, it's not always easy to go back, but at least I'm going to try and give an overview of something, of sort of the key development. I mean, I honestly believe this in this article that I put as there. I think David Tong, who writes these spectacular notes, said, it's the most important thing in theoretical physics in the last 50 years. And I think it is. But it's not the same thing as what you're probably used to hearing about. It's much more meta. And it is, let's see if the writing works. Okay, it does. The theory of theories. And what I'm going to talk about is something that is called the Renormalization Group. That sounds very esoteric. You probably forget the name group. It's not even actually correct. The word group is, has a precise mathematical meaning, and it actually doesn't belong here. I'll throw in a few words for those of you who do know what the precise meaning. The key word is renormalization that we're doing. And why I say it's so important, okay, it's a theory of theories. What it is it relates different theories. And not just qualitatively, but quantitatively as well. And in fact, so and I'll give some very specific examples, but you can use this to see what look like not just different theories describing the same things, but theories that look like they're describing utterly the same, utterly different things, are in fact have this underlying core. And there's a word, I'll keep mentioning it, but I might as well put it in here to say how important it is. It's one of the key words. If I succeed in explaining to you what the word universality means in this context, then I'll have succeeded in this talk. And so let's just keep going. So now you've probably heard all sorts of marvelous talks in the seminar series or elsewhere about all the stuff people do in very small scale physics, like understanding the quarks, say, some microscopic thing. But then they say, well, but quarks, we understand, you don't actually see a free quark. You see lots of indirect signals of a quark, but at least not in our macroscopic world. But we do see protons and neutrons much more simply than we see quarks. And quarks are bound into protons and neutrons, or nuclei to describe them, and other things. But of course, then you add an electron in and you make atoms. And then you put a bunch of atoms together and you make molecules. And then you make molecules, and then molecules all bind together into this pen that I'm having trouble with, or other stuff that you see. And, lots of physics deals with each one of these things. And we often relate them, and you're used to hearing that. But it's not at all obvious on why this is even possible. So what the Renormalization Group does is answer this question. So now, from now on, since I already told you that group was a bad word, and also because it's easier to write, I'm going to call it the RG. And then we'll get back to what the word renormalization means. So anyway, so why is this possible to relate micro to macro? If there's anything else I want to say here. And let me say one more thing before why you might want to do this. I mean, other than, you know, we're physicists, we just like doing things we find interesting. But there's a key buzzword people have been using recently, although the ideas go way back, what people call emergent phenomena. And this is when the macroscopic stuff looks very different from the microscopic stuff. And so, for example, to give one example, I'm not going to have any time to discuss the physics, but I thought I'd throw this in advertisement. And very possibly you had a talk, if you had a talk on topological quantum computers or something like that, topological something or other, you might have heard this fact, what's called fractionalization. And so what fractionalization is where the constituents of a system, you know, have some charge. Say, let's do charge. There's different kinds of fractionalization. We can do charge. So say, let's have electrons. So this is just electrons and they have charge E. But then in a certain, if you put two-dimensional electrons, you can actually put electrons in 2 dimensions. You trap them in an interface. There's 2 semiconductors. People know how to do this. And so the electrons are trapped at the interface. If you want to think in terms of potential energies, they have a very sharp potential energy right at the interface. And so they essentially don't propagate into the bulk of either of these semiconductors. So the electrons are roaming around 2 dimensions. Now you put a magnetic field perpendicular to that. And if you know a little bit about, they go in circles around that. But in the quantum world, much funnier things can happen. And one of the things that does happen, if you really turn the field up a lot and you have a really excellently done interface like this, is you can get fractionalization. And so what that means here is you can see particles that have charge E/3, even though there's nothing else in the system other than electrons. And this is possible only because you have lots and lots of electrons, even though they're all trapped in 2 dimensions, they're still 10 to the, I don't know, 8th or something like that, typically electrons floating around. And then if you look at sort of effective particles, so these another key word is effective. And these effective particles, or what condensed matter people call quasi-particles, have charge 1/3. And the only way to understand why this happens, of course, you know, is to relate the micro to macro. And as I said, the renormalization group is the. Okay, so this was the word universality. And this is one of the key things the renormalization group, the RG, tells you how to do. And so I said this already in the introduction, different physical quantities in completely different systems have exactly the same value. And so what do I mean by that? So I'm going to give 2 systems later on. One is that of liquid gas. Transition. I'll be much more precise about that in a bit. A certain special liquid gas transition, and you'll ask questions about how densities vanish at the transition, and I'll explain that very precisely. And you find some numbers are exactly the same as how the magnetization in a ferromagnet. Again, I'll explain a little more detail what that means. And some numbers, certain numbers, not all numbers, many numbers are very different. The two systems are very different, but some numbers are exactly the same. And this phenomenon is it. Now, so let me just say something, and this is what it means to universality. So let's step back again. I said at the beginning, you go back in history. So you may remember that they make a big deal in your first physics class, probably about Newton's universal law of gravitation. Hopefully they used the word universal, and it was really important because what Newton said is the fact that why the Earth goes around the sun and the moon around the Earth and Jupiter around the sun is the same physics as what causes objects to fall. And now, of course, they teach you that in your first physics class, and hopefully it's quite obvious. But if you think about it, that's not obvious at all. Why should those two things have to be the same? But yet he showed that going around was the same as falling on Earth. And now, yeah, again, we can act like that's obvious, but it's not, and that's universal, and that's why that word is used, and it's a good one. This universality is even a stronger form. Let's say these two systems, a ferromagnet and a liquid and gas, don't look anything alike, but certain things, if we measure them, will give exactly the same answer, which is pretty marvelous. Okay, and so as I keep saying, the RG gives a framework to let you do this, to relate physics at different length scales, like I was explaining slide before last, and thus get this universality. So let me say, sort of give a sort of summary of what I've said and where I'm going. Okay, so there's a word I'm introducing now for the first time, this word relevant. There's actually a precise technical meaning. It's one of those happy times where the precise technical meaning and the intuitive meaning are the same thing. And so one of the things I'll explain is when you're looking at a physical system, and you might think it'll depend on everything, if you're talking about, like I say, this complicated two-dimensional gas of electrons, well, you might be worrying, well, there's 10 to the 8th electrons. Where are all of them? What are each one of these doing? But it's telling you what the renormalization quantifies is why you can ignore most of the things that would describe the system. And so physicists have been doing this, of course, since physics began, ignoring most of this, reductionists or whatever you want to call it. But this now provides a precise framework to tell you why you can do it. And the happy thing is why we're not out of jobs, why we have something to do is because in many crucial cases, there's only a small number of these. So again, I'm going to try and give a little more precise notion of that. And then one consequence of these having only a small number, underline that again, small number of relevant parameters of things you have to worry about. Well, that starts to explain why universality happens, because even the systems may look very different. It may only depend on a few things. And in those particular systems, those two things may, all the details go away. And if you look at the right things, they're the same. And then what was alluded to in the introduction, and this will be kind of what I get to at the end, so we'll see how much time I have to babble about that. This isn't just some cute thing that many body physicists or people interested in electrons think. To make sense of quantum field theories, and that's a big chunk of theoretical physics, and what people often call fundamental physics, although I'll rant, I typically don't like that word. Maybe I'll rant later on by that. Anyway, the quantum field theories that are describing the nucleus, or even the weak interactions, or even things at smaller distances. These quantum field theories are essential to understand this thing. And in the initial formulation, people said, oh, it makes no sense, infinities. One of the great sadnesses of Dirac, who contributed so much to the early development of quantum mechanics and actually the beginning of quantum field theory, got so turned off by these infinities and by the very ad hoc solution that was done by Feynman and Schwinger and Tominaga, the thing they did in quantum electrodynamics, if you know a little bit about that story. Anyway, the thing they did was it was ad hoc. It was a hack, to put it mildly. And again, maybe I'll say a little bit more about the hack they did. And Dirac was so offended that he basically refused to ever look at this stuff again, which was a shame. The renormalization group did happen after he, before he died, but I don't know, he didn't. Wasn't impressed enough, but I hate this word. I get angry because you still see it in various places. Oh, you know, you have to throw out the infinities, and you know that was the way it was before 1970. But Wilson and the Renormalization Group explained how to do that. All right, so now let me stop now for pause, at least momentarily, for any questions. That was sort of a long, very broad introduction, and now I'm going to go back and try and explain some of the things I said a little more precisely, not a lot, but a little more precisely. But yeah, any questions on what I said so far?
Feel free to pop them in the chat, and I'll read them out.
Okay, nothing in the chat yet. Well, I mean, yeah, feel free, someone, you know, if it's pressing, you can interrupt me, and yeah, someone can put it in the chat, and then the organizers can interrupt. Okay. And also, yeah, okay, I do have a clock. Okay, good. So let me try and quantify some of the things I said. So I'm intending to go for about an hour, but we'll see. Maybe it'll drag. Oh, well, drag a little more. Okay, so physical phenomena. I mean, like I said, you know, physicists have to work, and you know, we can't keep track individually of even 10 to the 8th atoms, much less 10 to the 23rd atoms. So we have to simplify a lot, and luckily this works. And a key word, it's a math word, and I debated on whether I should say it. So many of you may have taken a class on complex variables, and so what the word analyticity means. Analytic means, if you haven't, don't worry. What it really means, it's a nice function of these things, differentiable and stuff like that. And in particular, it's single valued, stuff like that. Stuff like that. So it's nice. And it's not said enough, but it should be, yeah, it definitely should be said more. We all pretty much always assume the physics is analytic in these parameters. It's a nice function of these parameters, except, and we'll get to the key exception for at maybe special points. And one of the things I'll talk about is phase transitions, where these things. And so I decided, okay, let me give a few examples of this, just to see what I mean, and how far you can get. I mean, this is one of the just amazing things. You know, Ohm's law. Well, you have a circuit, it's got a battery, it's got a voltage. That's just how hard it pushes the electrons when they go through a battery. And you make a circuit, and you connect it to something, your TV or whatever. And when you connect it, current flows. Now there's a crucial observation you can make. If there's no battery, or in our case, you don't plug it into the wall, there's no voltage, so there's no current. Nothing happens. So say you just have a very weak battery. Well, if it's analytic, it depends nicely on these things. What that says is, maybe for small current, the volt, I should have said I is proportional to V, sort of. so small voltage, I is proportional to V. That alpha symbol means proportional to. Why not? Seems nice. If it's nice, you'd think, you tweak it's just linear. And then, well, so you just now assign a constant to that proportionality and you get V equals IR, Ohm's law. I mean, that's really all Ohm's law is. The thing is why that's useful, because it works, at least, a lot of the time. It's a good approximation to what's really going on. And then you can forget all the complicated things about the interactions of the electrons in the wire, how the battery works and all that. You can figure it out. You can parameterize this relation just by this one number, the resistance. And you do experiments and you see for your resistor, it more or less has just a value of a single value in ohms. Now, if you really are careful, when it heats up, R changes, all this complicated stuff, but you get a lot of mileage out of that. So that's one of the examples of how we just pick out a few parameters and it works really well. I'm going to give a slightly more sophisticated one. Just actually look at my notes so I don't screw it up. There we go. All right, so let's think of a gas. Again, you in high school chemistry heard about the ideal gas law, and I'm just going to give you the sort of lowbrow physicist way of getting it without having to think a whole lot. All right, so let's think, well, what are the physical quantities? You've got a gas, all right, it's got a pressure. How hard it pushes on the box it's in. All right. Well, it's got volume, the gas is in. So, and I'll do it the physicist way. It's got a number of particles. That's how many particles there are there and trapped in the box. It's trapped in a box, nothing much else is happening. And then the last parameter is the temperature. Now I'm going to write this. This is the one thing you need to know. We give units of temperature in these funny things, Fahrenheit or Celsius or whatever, or Kelvin if you're being more precise. But those are funny units, and what we would like to relate it to is an energy. And so again, a long story, but if you know a little bit about thermodynamics, you know that you can think about temperature as an energy, and there's this constant, it's called Boltzmann's constant. It's a number. Okay, so that's the one piece of physics you need to know. Well, then just dimensional analysis. So you just look at pressure has a unit force per area. Volume has units, well, length cubed in our world. Number of particles doesn't have units, it's a number. I just want a big deal to say, well, energy's there, energy's energy. So anyway, you sort out the units and you get that the pressure then has to be proportional to the volume times the temperature, and then this constant there. And actually it turns out basically this constant is defined so that this is actually equal, not proportional to. But you get this anyway. And again, it's saying we're forgetting all this stuff. And I want to emphasize, but that's an approximation. So one thing you can do, and the simplest approximation you might make, is let's worry about the volume of each molecule. Now, the gas doesn't fill the whole box. But remember, pressure comes from molecules hitting things, so it might matter. And that's B. And so we can't do any better. We can't now, there's too many, there's an extra parameter. And so we now can't get an exact answer like the ideal gas law. But what we can do is correct it, and we can say that the pressure is, oops, sorry about that. So that, say that the pressure is equal to that, and this is some function. So we've reduced a seemingly complicated problem to one function. And I wanted to show this because this is the kind of thing we look at using the RG, is these sorts of functions. Okay. All right, so that's a setup. All right, so, well, I mean, so that's sort of the setup of starting the quantitative setup as opposed to the qualitative one. All right, so now let me start to explain the physics. All right, so this kind of simple approach, so what doesn't always work is this kind of simple approach. You just write down the parameters, you mess around, maybe you do an experiment, maybe you do a calculation. If you're smart, you can calculate. So like that in the example I just gave, again, if you've taken a class on this, you may have heard of the van der Waals approximation. And van der Waals assumes a particular form for that function and then does some stuff. You check it with experiment. You can kind of see, again, it's kind of this series like I did with V equals IR. But this doesn't always work. And here's the key example where it doesn't work. And these are called critical points. So this is the phase diagram of water. You can tell it's water because the funny thing about water is that line tilts that way. So as you, you see the practical effect of that is ice floats. Ice is less dense than liquid water, which is unusual for a solid and liquid. But that's not what we care about today. What we care about today is what happens here. It's really funny. Okay, so if you look at this phase diagram, this is just increase the pressure. As you increase the pressure, you think things, you're going to make things more dense and then they might solidify. And indeed that happens. You start out, we're used to, water freezes at 0 degrees C, but actually at higher pressure, you see it freezes at a lower temperature. There's the 0 C and it freezes at a lower temperature because you're pushing on it, you're helping it freeze. And the same with when it evaporates, and that's this curve here. So this is what we're going to be concerned with now. This is the solid liquid transition. And you see, maybe not surprisingly, as you increase the pressure, it wants more to be liquid. So as you increase the pressure, the temperature goes up. Now this thing, notice this is not to scale at all. This picture I stole from somewhere. Did this to make it clearer. So this is our usual atmospheric, at atmospheric pressure, this 101 here, kilopascals is atmospheric pressure. But here, what happens is, well, okay, so what happens is obvious. As you increase the pressure further, or then you have to go to a higher temperature to boil the water. But now something happens here that's really strange. And now at that point there, so let me just kill that and I'll circle it again so you can see it well. All right, at the critical point, solid and liquid are the same. This line just stops. So this color here is just a guide to the eye. There's no way to tell the difference between water in its liquid form and water in its gas form once you're up there. Now notice this is a huge pressure, a lot bigger, 200 times atmospheric pressure. So it's a huge, you won't see this. But when you go to this huge pressure, you can't tell, because if you wish, the gas and the liquid get so dense. Now you could say, if I'm down here, yeah, it looks like a gas, it's not dense at all. If you go way up here, if you go way down here, it's not dense. We go up here, it is dense, but in the middle, you can't tell. And the point where that happens is is called the critical point, where where there's no distinction. And what the key physics of this is physics on all length scales matters. Okay, and so that means you can't separate micro from macro. They're all tangled up. And I'll say a little more about that, but one example of this, and I'm not going to mess with embedding a video because screw it, but you can just go on YouTube and look up for the key buzzwords are critical opalescence. And you can find videos where what happens, they usually don't use water because it's such a pain to deal with. You can find things that do this at sort of much lower pressures and temperatures, so you can just do it in the lab. But what happens is, what critical opalescence means, you look at water around here and it looks milky. It's not clear. Because I mean, either water vapor is clear, we see through it all the time, and liquid water's allows light through. But what happens there is, because all this physics matters on all length scales, when the light goes in, normally it just goes through, but now there's molecules vibrating at these scales and it scatters the light. So the water gets milky. And that's okay. And this turns out to be the key thing for understanding. So one thing that happens at these points, lots of interesting things happen there. I told you critical opalescence. But now, again, I use this buzzword analytically. So non-analyticity occurs at these critical points. And so what that means is the following. So what this is, what little v is kind of the inverse density. It's the volume per particle, right, V over N. And you can ask, at a given pressure and a given temperature, how, at given pressure, given temperature, how much volume does this take? Now, a gas is typically less dense. So V is, so V gas would be, this is typically bigger than V liquid. So the thing I wrote is going to be negative. And now I look just along this coexistence curve. So along here, both water and gas can coexist. You have both water and gas together, they're happy, but the water is denser than the liquid. And so V gas is greater than V liquid there. So you follow there up to the critical point, and now this vanishes. So at T equals TC, TC is the temperature of this point there. It's temperature 374 for water. At the temperature, the two are indistinguishable, so this difference is 0. But then they're, aside from there, it's different. And you ask how it vanishes. And here's the amazing thing. So here's some universality. No matter whether you look at water or all the other things you'll see in the videos, all the other chemicals whose names I can never remember in the videos, you always measure this same exponent, 0.32. It's not 32, sorry, 0.32. You always measure that. So we're seeing two things. First of all, this simple stuff like V equals IR breaks down. This is crazy number 0.32, and you can get it to more. That's both an experimental theoretical result. It's actually known better than that theoretically now. But you already observed the same number. So on one hand, things are bizarre. On the other hand, they're not nice, I guess, by my definition of analyticity is nice. And then they're really nice. You get this universality. And then, as I mentioned at the beginning, you get relations to systems that are completely different. So what a ferromagnet is, it's a bunch of spins. So there's spinning around in a quantum world. Again, if you've taken a quantum mechanics class, you know that these things get quantized. And I'm going to take we don't have to do that. So we've just got a bunch of atoms spinning, or molecules spinning. And so they're spinning around, and you ask, well, so what direction do they point? Now I'm going to take a very simple one with this word icing, which maybe you've heard, maybe you haven't. I'm going to take a simplified version where they just point up, which I'll call plus or minus. And so what happens in a ferromagnet is that the interactions want to make the particles line up. Or they can line up that way. So this is what the interactions do. Now, of course, but temperature, heating it up, you're throwing all this energy in, wants to make it look any which way. So now if you look at the average number, so what the M is, the number is the average number pointing up. Say, or the average number up minus the average number down, doesn't matter. And what you'll see as a function of temperature, this magnetization looks like this. So this, and it's saying, so it's zero temperature, and that experimentals can go to essentially zero temperature now, almost zero temperature. They'll basically all be pointing up or all be pointing down. So then we put that for magnetization, maybe I'll put that there, just to avoid confusion. But then as you turn up the temperature, less and less pointing, but then there's an abrupt place where it stops. And if you know, again, what analytic function is, this ain't analytic because it's coming down and then just stopping. It's not differential. It's continuous, but not differentiable. And the remarkable thing is, you plot this curve and you get the same exponent as you approach the critical temperature. Exact same. And that's this even broader form of universality. So first of all, we had universality in this case, in the liquid gas case, where it was different materials. But in the full case, sorry, in the magna case, you get even bigger universality. All right, so okay, that's another good stopping point again. If anyone has any questions, because now I'm gonna broaden again, but I wanted to be very precise about an example, and then I'll now try and explain what the RG does to explain this universality and other things. Mm-hmm.
Nothing coming in yet.
Good. No, just I always try and get people to ask questions because it means then I have to prepare less material. I could be more discursive, but sorry, okay, that's fine.
There will be more at the end.
Yeah, that's right. Okay, so hopefully I haven't lost people. And now I'm going to try and so this is the historic slide. So Wilson, I should say, this is Ken Wilson. Who for many years was at Cornell, then he moved to Ohio State after he got famous. He was by training a particle physicist, but one of his great strengths is he was just open to good ideas. And so very much what he did was a hybrid between what was being done in particle physics and what was being done in statistical mechanics and what was then called solid state physics, not condensed matter physics. In particular, he built on this prominent work by Gell-Mann and Lowe in the 50s, and then in particular by Leo Kadanoff, and I'll explain a little bit about what Kadanoff did. And also Whittam talked about scaling. And so there were seemingly two very different problems. Okay, so one is defining field theory, and that was these infinities that I alluded to before. And I'll just say two words for those of you who may know what perturbation theory is. So perturbation theory says, well, you start out, you assume you have some weak interactions. And in fact, in the QED, the quantum field theory of electrons and photons, that's a good assumption. The interactions aren't, the electric charge isn't that big, if you wish, and aren't that strong. And then so you first assume it's really small and you do a calculation, and then you correct it, by adding a higher order term in some expansion, you keep going. But the mystery they found was that first order does great. And that's why I say Feynman and Schwinger and Tomei kind of had to cheat. And for the following reason, okay, first order looked great. And that was known in the 30s, before Feynman and Schwinger, when they were boys. But then smart people in the 30s recognized, well, then let's calculate the correction. And this is where they got infinity for the correction, or seemingly got infinity. And it was, and so they didn't know what to do. And then the war happened and everybody went off and did other stuff during the war, except for Tominaga. So he was working on this throughout the war, but then Feynman and Schwinger came back and after the war, and that's when they sorted out. But as I mentioned at the beginning, it was a hack. They basically took two things that were, in their definition, infinite, but subtracted them and found that it was finite, but without being able to really precisely show what they were doing. In retrospect, we can see what they were doing, but it was, cheat is a strong word, but it was definitely a hack. Okay, so that was the thing, and people were very baffled. I mentioned Dirac just decided this whole thing was nonsense and wasn't going to pay any attention to it, unfortunately. But what Wilson, did was then notice what people were doing in condensed matter physics to understand critical phenomena, held the key. And the key was this different length scale things. Because what was happening, these infinities were happening at very short distances. When you were trying to take into account the physics of short distances in these calculations, you would get quote infinity. And so he realized, and in particular, Kadanoff's work was extremely influential in his thinking. So I wanted to explain just a little bit about what Kadanoff was doing that then led to Wilson's great insight. So Kadanoff was saying, all right, well, look, we don't care about what's really going on at a microscopic scale. We're just trying to measure, is this magnet going to stick to my fridge? It's what the magnets on your fridge are ferromagnets. So I just want to know, what's going on in this macroscopic scale. Again, remember this thing I said at the beginning, this micro for macro. And so what Kadanoff said, let's do something. Okay, so here's my magnet. So I'll just say, well, on each site, so I'll do this icing example where it's plus or minus at each site of some lattice or whatever. I drew the square because that's what's easier, but that's my system. And I've got lots of 10 to the 23rd of these things, or 10 to the 8th, got lots of them. So obviously I don't care whether this particular, or whether that one, pick any particular atom is up or down. I just want to know what's happening on average. What Kadanoff said is this, well, let's now, we've got a big system here. Let's now divide the system into blocks. And he said, let's average over each block. Okay, and then I'm just going to talk about one big spin for each block. So let's use a different color here for a change. Let's try. So then I'm just going to have like a spin plus or minus, say, in that block. Already it's problematic. An average isn't always going to be plus or minus, but maybe we make some approximation. And then you might hope, because we only care what's going on large distances. So there. And then you keep doing this. So let's do another one. another color here. Now then I average the average. So we've got in my system here. I average the averages, and each one of these has individual ones. And then try and come up with a key word again is, I think I said this at the beginning, an effective theory. And this is trying to quantitatively relate the microscopic to the macroscopic physics. And remember with the critical point, why critical points are really important in this story, because I said that's the point at which all these length scales contribute. And that's the reason why these things are not analytic. The physics is not a nice function of the parameters of the system. And so that's what Kadanoff did, and had some success, at least qualitatively started to understand. And he also understood then why naive things quantitatively broke down to understand why that's 0.32. There's another part of the prehistory I should mention is goes under the name of Landau theory from the great Russian physicist, and that's again an effective field theory. A field theory is one that you might say is much nastier than what I talked about here. Field theory has degrees of freedom at every point in space, so lots of these. But so that sounds even worse. How do you do that? But of course, then everything's continuous, and so it's much nicer. And this is possibly why the field theorists were doing field theory, and the kinds of people doing this. And it wasn't Wilson wasn't the first person to observe. For sure, wasn't the first person to observe how the two could be related. Landau was the key things. But Wilson then realized how to put all this stuff together and do it quantitatively and precisely. And so that was this great accomplishment. And so one of the things he does, so these words I mentioned at the beginning, or one of those words I mentioned, relevance and irrelevance. It tells you which parameters to keep in this. And this is a quantitative way. So it's not just your own personal opinion. There's a calculation. I should have said, get that calculation you can do, or at least sometimes you can do, to see what your theory is. And so again, this is what I keep saying, it's a theory of theories. It tells you which theory you should look at if you want to understand a certain piece of physics. So again, that's what I'm doing. So the rest of this slide is just what I put before. It tells you, well, which parameters are relevant. So let me go back to the Kadanoff thing. So we have these other spins, but you can easily see when you follow what Kadanoff did and try to quantify what Kadanoff did, what you'll see is not only this point of just describing them as plus minus starts to get problematic. So that when you say, all right, well, then instead I'm going to talk about a continuous variable and start thinking about a field theory. So that you can solve. But it gets worse than that, because what you see is you get longer and longer range interactions as you do this. So even if you start out having only nearest neighbor interactions, you get longer and longer range interactions. And that's what Kadanoff say. I mean, it's easy to see. And you can say, well, let's just throw out the longer range ones. Maybe they don't matter. But what Wilson does with the renormalization group is this calculation I keep mentioning. It tells you gives you an honest way of saying which one you can do. In other words, which ones are relevant and which ones are irrelevant means, well, I can forget them. They do affect the physics. It's their physics. But if you're just looking at things at very long length scales and certain properties, universal properties, there's only a few of them, at least if this works, and typically only a small number, which is remarkable. And so again, this now tells you why there's universality. There's only a small number of parameters. I'll just repeat what I said earlier. When you do this procedure, you get rid of the short distance degrees of freedom. You remember only what's going on at long distances. And you throw out all the irrelevant parameters. Well, maybe it's not, at least less surprising, that you get this universal physics. So in field theory language, I wrote down one field theory description of the liquid gas transition, and at least in the region of the critical point. All right, another theory, another theory down for what's happening when the magnetism in a ferromagnet, when you heat up your fridge magnet enough and it stops being magnetic. But when you simplify them by, again, only asking what's at long distances and throw out all the irrelevant stuff, you end up with the same theory. Now, the theory doesn't describe everything, but it describes what you let it, the long distance things that you've built in there. Okay, so I guess I've gone, I've gone a little less than an hour because it started late. So now for the last part of the talk, I'll try and say a little bit more about this infinity stuff and why the renormalization group does. Okay. Oops, that was my last. This is my last slide. Let me, sorry, let me get a blank slide. Oh, I'll go back. All right, blank slide in there. We can just kill it. There. Okay. So now I want to explain a little more detail on how this solves interaction. So I already said a little bit, which I'll repeat, that, well, you do a simple calculation, sort of the leading order calculation. So say a theory of electrons and photons. And it actually gives something kind of sensible. Compute the Lamb shift and all this stuff. But then now when you try and do the first correction, once you build in field theory, you get these infinities. So let me first explain a little more detail what's going wrong and then how Wilson and the RG fix it. All right, so you've got an electron. This is my electron. We're still, we would like to treat the electron as just a point particle. They're really, really small. But when you do that, you're in trouble because the field, the electric field, due to an electron, goes as 1 over r squared as you go near the electron. Well, electrons, like I say, are really, really tiny. In fact, no one knows, in a sense, how you can't measure the size of an electron, not through conventional means. And, so this is blowing up. If you ask the electric field due to an electron, it's going to infinity. And okay, so in classical physics, so what, we just won't go to r equals 0, it's all fine. Classical physics works, but in quantum physics, and relativity, well, okay, so let's put these things together. All right, well, first of all, we have because this is big, we have large energies. Let's go back to highlighting right here. So we get large energies. Okay, well, large energies means we have to do relativity equals mc squared. But quantum physics tells us we can create particles. So we can always create photons. We could also create electron positron pairs. If you don't know what positron is, it's like an electron, except it has the opposite charge. So you create these pairs. And this is inevitable. The theories all predict this, and it happened, and it happens in nature. So what's happening is when you get an electron here, there's my electron, but then what happens is I can be pair creating all these things around. You would think, at least if you follow the theory, you pair create all these things because this electric field gets so large there. You pair create these things. And of course, also if you want to get more complicated, well, then the pluses want to be a little closer to the electron because they're attracted where the minuses want to go away. So this is what the people in the 30s were trying to compute. And some of the greatest minds of theoretical physics were trying to compute this. And it was a mess and they couldn't make any sense of it. And that's the quote infinity. But okay, so that's the problem. That's at least a very crude version of what the problem is when you put all these quantum physics and relativity together to try to describe electrons. So, but I drew this picture. So when we're doing sort of Wilson stuff, remember I said, well, and of course they Kadanoff and then Wilson stuff. You say, well, let's now, again, we don't care what's going on right at the electron. We can't get that small. We can't get to 10 to the minus 33rd centimeters or whatever, at least not very easily in our world. So why don't we sort of average over all this? And so what happens, we've turned the electron problem, what seems to be a single body problem, we've turned the electron problem into a many body problem. And I didn't even talk about the photons. I'm just talking about electrons, but those you got to worry about too. You get lots of photons. And so we've turned it in. So even though we have just a single electron, fine, I'm just not electron gas like I was talking about before. I've still turned it into a many body problem. And then I can do the averaging, the Kadanoff thing. And this is how the RG makes sense of these theories. In fact, the RG is needed to define these theories. And so that's really the proper statement. The RG is needed to define these theories. And so what it says, and if you wish, where the quote infinities came from, is because the people didn't understand how to relate the microscopic parameters to the macroscopic ones. And the renormalization group gives you a precise thing. And the point is, we do experiments, and we measure these, even though they're an accelerator, this would still be the macroscopic parameter because it's not at the scale of the electron. But in the theory, then, if you define the correct microscopic parameters, then you get the correct macroscopic parameters. And it gives you a precise way of doing that. And there's a lot of technical complications, needless to say, but it makes the theory define. It enables you to give a precise definition of the theory, at least a precise perturbative definition of the theory. And that's the RG in a nutshell, what it does, and why this problem, what was Wilson's genius realization, was the same problem as critical phenomena. And there's so the point is, so what it turns out, something that even I think many people who do particle physics may not fully appreciate, is that to even define a field theory, you need at least a nearby critical point in your model. So it's like where the electron's mass vanishes and things like this in order to make sense of it. So it really is that essential. And then, of course, it's needed to do the calculation. So one of the things you'll see, for example, is that depending on how you measure a coupling, and there's one you may have heard of. If not, it's okay. This is basically the charge of the electron. And a fancier word is called the fine structure constant for that. And if you measure that in an experiment, its value will depend on precisely the energy scale at which you do the experiment. The word people use, it's running couplings. But anyway, so it's not really constant. That's why I put constants there. It depends on how you measure it. So that's why you beware of papers. I mean, there's crackpot papers that appear on, well, we get most of them off archive, but that people claim to have a formula for the fine structure constant, but that isn't even really a defined thing as a single number. It's a function, and it's a function of the energy scale at which you measure it. Right, I think that's, let me just glance at my notes in case there was anything really, truly awesome that I wanted to say. But yeah, good, let me say, let's get rid of this. Let me say one more thing, and then I think we're about an hour now. Good, okay, good. I'm gonna stop in 1 minute. One last thing I wanted to say is, so the scaling type things that I did, the scaling functions, like I did for the ideal gas and things like that, still work. But the thing is, the RG tells you there may be hidden parameters. And these hidden parameters are what relate micro to macro. And these hidden parameters are also what you need to understand universal behavior. Okay, I will stop now. So I will take verbal or written questions.
That's great. Thank you so much. Yeah, we got a couple of questions. I got a couple by direct message, so I'm going to read them out. The first one, I guess the title of your talk maybe answers it, but I'm still interested in hearing you talk a bit about it. So is RG a theory about nature, or is it more of a framework that allows other theories / calculations to be made? That's the first question.
That's a good one. Yeah. Well, that's a good question. I mean, actually, a philosopher friend of mine, I think I came to talk, he probably could answer that. I think that's how, yeah, I don't have a good answer to that. Certainly it is a framework certainly it is a framework for relating different theories. On the other hand, so that part is certainly true. I mean, that's what it is. But like I say, it's more than that. It doesn't just say theory A is equivalent to theory B. It tells you in both theory A and theory B how to do certain kinds of calculations, right? So I mentioned this fine structure constant, that basically the charge of the electron, and how it depends on distance. It gives you the tools needed to do that. So now maybe you could say in the individual theory, there's other tools. So in that sense, it's an adjunct. We've got a theory of the electron, then the renormalization group is the tool used. So maybe it's both a framework and a tool. I think that's the best I can do with that, all that. Is that, Yeah, is that
Yeah, I suppose you could
close
say
to
that
what
about
you
many
want?
things. It's not just, I think, something specific to RG. But yeah.
So the to answer, there's a question in the chat I see. Is that does that mean existing theories are fundamentally flawed? It means that I don't like the fundamentally flawed. What it means is you have to be really careful in how you define the theory, if you care about these things. So I kept mentioning, well, you do the first order calculations, the sort of leading things, and they're fine. And so if that's all you need to do, that's all you need to worry about. And what you've done is fine. But if you want to push the theory further and then get it, well, then it's saying that your initial definition really isn't the right one. I have to now think harder and think about how to relate micro to macro. And the key word, I'll use the technical word, is you have to regulate the theories, as you may see and things. So you have to basically come up with a way to define the theory, and regulating the theory, maybe putting it on a lattice like I drew those pictures. Sometimes there's things that's called a momentum space cutoff, like you just pretend that there are no momenta, which is kind of like putting higher than a certain thing, which is kind of like putting on a lattice. There's fancier ones that's called dimensional regularization for non-obvious reasons. If you pretend a theory is in 3.9 dimensions instead of 4 dimensions, it makes some things easier. That's a tough one. Anyway, so I think that's maybe a better. So I wouldn't say it's flawed. It just means if you're interested in certain things, you have to be more careful. Okay.
We also got another question directly, which you're not going to be able to see. A short one. Why is the word group a misnomer in RG theory?
Oh yeah, I said I would do that. Oh, it's because you're forgetting stuff. A group is invertible. If you learned any what a group is, group says, okay, I can take two things in the group and multiply them, get another thing. But a key thing in the definition of what a group is, it's invertible. And so the renormalization, sorry, I forgot to give the buzzword, so good, thanks for asking. Or the renormalization is exactly this thing of understanding how to relate micro to macro. It's saying these couplings, like with the electric charge, I can't just define at one value. I have to ask what values. And so that's what the renormalization means. I have to change these couplings. That's a good word for it. And when people first did it, they said they thought it was a group. So you could zoom out and you could zoom in, but the catch is we're forgetting lots of stuff. That's what I kept saying. These irrelevant parameters we're throwing out. So you can't go back again. Only by theory can you go back again. So in other words, you can see, you do an experiment and you can try and work and understand what's going on microscopically, but you don't have all the information. So it's not a group, if you wish. When you do this transformation, this like removing all these spins or averaging, you're forgetting things. You can't invert it, and that's why it's not a group. But the name stuck. It's Wilson should have ditched. It wasn't him. It predated him and earlier things. And if you read his Nobel lecture, he even explains where the name came from as a way of saying, I'm not to blame for the name, but he should have ditched it and people would have followed him, but he kept it. Right. So yeah, it's got some other ones. Which one would you like me to? There's some in the chat. I don't know.
Yeah, Dylan has also raised their hand. If this is, feel free.
Okay. Well, people can say them to me. Or
yeah. Thank you. Thank you so much. It was a really nice talk, and it was really easy to follow. My question is, so you mentioned that so for Feynman and Springer, for instance, they tried to tackle this problem by sort of canceling out infinity. So I suppose what you meant was in the final picture that you drew, you would cancel the energy contribution from the electron and the positron, right? And if that's the case, I cannot really see the difference between what they did and the sort of averaging that the renormalization technique does. For me, at least, I feel like it's sort of the same thing, which obviously is not. So maybe you can comment on a bit on that.
Yeah, because the point is Yeah, so I said it can create these pairs, but the point is they effectively change the force, because now this is an extended object, if you wish. This is a pretty bad explanation, but it's the simplest one I can come up with. So it's this extended object. So you won't, if you now just say, here's the, what's the charge here? And because, like I say, the minuses, the pluses want to get closer and the minuses want to get further away from the thing. And so yeah, the pluses and the minuses want to get, the pluses want to get closer, the minuses want to get farther. So when you actually then look at what the charge is, you won't measure exactly E. You'll measure, something else times E. And in fact, when you did the calculation, you end up getting it infinite, which is bad. Because the pluses really want to move close. And so it's not, they don't, the point is they don't all cancel because they spread out. And so I think that's the best I can give.
Thank you.
Great. We have a couple of more questions. I read all of the direct ones out, I believe.
Well, no, I've got a bunch in the chat.
No, I mean, yeah, that's what I'm saying. So if you want, you can just
oh yeah, let me look at the chat. Yeah.
And then if you read them back out, that's great for the people who watch the
so I'll read it
recording.
out. So someone commented, I think this is more or less the answer I gave. So, but yeah, I got this person. This is the last one, but since I'll just reiterate something, is RG a means to relate micro to macro, but during the averaging, there are some phenomena being dissipated by the most significant phenomena in the group. There will be no way for the RG to recover the lost phenomena. Yeah, in that sense, yeah. No, of course, we theorists, we go think, all right, well, how did, what's our microscopic theory, and then is there some way of testing the law? They're not necessarily lost. You just have to then refine your analysis and say, okay, even though this parameter is irrelevant, I still want to understand what it has in the physics. And there are ways, the RG gives actually a framework for even doing that, even though it's irrelevant. It says, all right, if I go to shorter distances, I can look at these things too. So in a sense, they're lost if all you're doing is looking at the macro thing. But we theorists can try and go back up, and then of course we can suggest to experimentalists, go look at this, and then you'll be able to see that. So yeah, so that one got it right. Right. Let me. All right. So yeah, sorry. Let me go back. Make sure I go back. I'll go back to the beginning. Is the inference that quantum fields aren't fundamental to particles are? It's. I think. I don't like the word fundamental because it means what you want it to mean. I mean, I'm not. Because then, half the time when you discuss it's just what you mean, what you personally mean by fundamental. I mean, it's a nice sounding word. The string theorists would say string theory is fundamental. The reason, if that's what happens, and the reason is because if you put quantum field theory together with gravity, what happens at short distance again gets infinite, and this time the RG doesn't fix it. This was actually something Feynman in the early 60s tried to now apply quantum field theory to gravity and saw that it didn't work, and basically it doesn't. You can basically prove that it doesn't work, and you replace things. Instead of having the quantum fields, you at very short distances you have strings, and that at least might allow us to do quantum field theory and gravity together. But but who knows? And so yeah, I don't know what's fundamental. Anyway, so do that. All right, what's the critical point of electron production? Per example, just set the mass of the electron to be zero, which isn't physical, but it's nearby, and you have this small coupling, and that's what. So you also set the interaction. Sorry, I should say you also set the interaction to be zero. So you set the electric charge to be zero and the mass to be zero. And then you've got you've got photons. They don't interact with anything, and you've got electrons which don't interact with anything. So it's a very simple theory, but it is critical. So if the fine structure constant, or as the formula 4 pi epsilon h bar Ca equals E squared wrong. If I said the fine structure constant isn't constant. Well, what people mean by that formula when written down, what they mean is if you're measuring the electron charge at low energies in R, if I did a lab experiment, what I would measure the electron charge to be. And then that's fine. And that's what they mean by that. And so that's okay. And so in fact, the best, for E squared over H, for example, the experiments related to the ones I mentioned with the fractionalization are the best experimental way of measuring E squared over H, and without the C, but E squared over H. And in part because it's at low energy and none of these things. So it's not, again, it's perfectly acceptable to say that if you're not talking about what's happening in an accelerator, that the formula E squared equals H bar C times 4 pi epsilon, so times alpha, sorry. Well, alpha is the fine structure constant. So that's, if you want to define that to be a definition, that's fine. But I mentioned these crackpot papers, but then you have issues. All right, do you mean the one you actually measure in an experiment at zero energy? Do you mean the one you calculate in QED? Do you mean the one you calculate in QED with strong interactions also thrown into the mix? And anyway, so there's, when you start to worry about it at that level, and experiments measure these things nowadays. It's one of the greatest correspondences between theory and experiment, measuring the fine structure constant, and all these things have to be taken into account. Okay, yeah, I think the next question, in the search for space-time with quantum properties, what role does the RG play? I think I sort of answered that. And so, I answered part of that question, I should say, in saying, well, people look at string theories, various other things, quantum foam and stuff like that. The RG is the framework that, again, still works with string theory, that tells you how to relate whatever your favorite microscopic theory, whether it may be string theory and which D branes you want, how do you relate that to the quantum field theories you get at the level CERN can do experiments, or maybe even higher. And that's where most string theories run aground, because string theories need, for example, this exotic symmetry called supersymmetry to make them nicely behaved typically, but it's not observed yet in any accelerator. And so it certainly doesn't exist up to the energies, at least, that CERN can go to. So the RG is what tells you how to relate these two. And the RG is what lets you say, ooh, we still don't know a string theory that describes our world. So all that. Is there an analogy to liquid ice phase transition in quantum field theory? Yeah, I mean, there's, maybe the simplest one is exactly the analogous to the magnet. And this is in these great triumph of particle physics in the 70s was understanding the weak interactions. So there's strong interactions, there's electromagnetism, and then in the 70s to the weak interactions. It's what's responsible for beta decay and things like that. It's much weaker than the other ones, hence the name, and that's why it was very hard to understand. And quantum field theory describes it, and you may have heard of the Higgs particle, which was famously discovered experimentally finally a few years ago. So it was most of the triumphs from the 70s, but the last piece in the puzzle, the Higgs itself, the Higgs boson, was only described in the last decade or so. And so what the Higgs does is, if you're an energy scales below the mass of the Higgs boson, well then a symmetry is broken. And the analog in the magnet example, I went through this very quickly, but remember I said at low temperatures, either they like to line up or line down, but there's a problem with that, because that breaks the symmetry, right? Because either they're all up or they're all down, or mostly up or mostly down, but it breaks the up-down symmetry. It's called spontaneously breaking in the symmetry. And so you have a phase transition, if you wish, if you're doing weak interactions at finite temperature. At low temperatures in our world, they'll be broken, but if you go to high enough temperatures, they become unbroken. And there's other things you can talk about, confinement transitions and all that, when the quarks become unconfined and things like that, which may not happen ever. So that's I think the weak transition is the nicest thing, and if you look in a field theory textbook, they use the ferromagnetic example as a way of explaining what that transition is. I think I got all the questions.
I think you did. There's another person who messaged me directly who'd like to ask a question directly.
Hi.
Directly. Hi.
Okay.
Hi. Cool. Hi. Yeah, Professor. It's a really great talk. I have maybe a more mundane but technical question. So if I look at the Ising magnet, the Ising transition, and the liquid vapor transition, so you mentioned that they're in the same universality class. But if I view from the symmetry point of view, and we know symmetry is a very powerful tool, it constrains how the free energy should look like. And this gives us a sense of why we have universality. But part of the reason is the symmetry. But here, with the Ising, we have this Z2 symmetry. But for the liquid vapor, it doesn't seem like we have this. So
yeah.
would you comment a bit on that?
Yeah, it's not obvious at all. Yeah, it basically, yeah, I'm trying to, I mean, there's not a difficult calculation. I'm going to look at my notes here and see if there's a way I can, offhand, I'm trying to think of a quick way to summarize this calculation. And I have some my notes.
I'm sorry to put you on spot.
Oh, no,
that's probably something I can look up in a textbook.
No, it's, well, it is in a textbook. You can look at Carty's book. I'm trying to think of, I mean, it's just so if you, it follows by, I'm just trying to think of a way to say the symmetry. I mean, so the calculation follows by, you think of your gas as like living on a lattice, and you make the particles hard. So you have either one particle, I think this, let me just say it this way. When you think of a lattice gas, okay, so you have your gas, instead of living everywhere, it just lives on, they just particles live on sites, and you make it hardcore, since particles don't like to get too close together, so that's okay. So either each side of your lattice is either occupied or unoccupied. Okay, and so then you get so that's a two-state system. We can call occupied up or plus, or unoccupied minus. Now you made the key observation, which is there's what's the symmetry? Well, when you start to write down the interactions, you see basically you can rewrite the interactions in a fashion so that it's symmetric. In other words, basically it only cares whether the two sites are occupied or unoccupied, and you get this. Basically, you see that it's you can shift the energy and it doesn't matter. And that's not a good answer, because that's a spectacularly good question. Okay, I will have to think. Yeah, I'm supposed to be writing.
I think this is a very great comment. Thank you.
Maybe that's the reason I never wrote that bit. And so, yeah, I wrote a lot of this stuff I've written up for a book I'm allegedly writing. And maybe the reason I never wrote that bit up is because I never liked that explanation, and you've now found the reason why. It's not obvious why you get the symmetry. You go through the calculation and it's obvious, but a priori it's not. Yeah, so the key thing is to think a two-state system, and then when you turn that into a two-state system, and then you turn it into nearest neighbor interactions, and it all kind of looks the same. But it's not obvious. I agree.
I
Sorry.
Yeah, but that's a really great comment. Do you mind if I quickly add a follow-up question on that?
No, not all people can. People can abandon ship, obviously.
Yeah, I was a little bit reluctant in, first of all, asking this, because I think maybe it's going through the calculation, things become crystal clear. But I was wondering if there is a intuitive way to put it, to resolve this seemingly conflicting stuff. But I was also having an attempt to rationalize this, but I'm not sure if this is right. So if I put it forward, maybe you can tell me whether this is right or not. Can I think about the term that explicitly breaks this Z2 symmetry? And of course, I may have to do some calculation, but turn out I argue that it's actually irrelevant.
No, it's not. It's relevant.
It's okay.
Yeah,
Okay. So
it's in the ferromagnetic language. It's adding a magnetic field.
Okay.
So I mean, a ferromagnet sticks to your fridge without.
And that corresponds
putting
to
another magnet nearby it.
adding a chemical potential in the lattice gas model.
Chemical potential in the language, yeah. And so that changes things. No, but you can incorporate that into the RG. So it's very relevant, and you can incorporate that in the RG. Yeah. Like for example, in the ferromagnet, it would wreck the, take you off the critical point.
So based on what you said, does the liquid gas transition has the Z2 symmetry?
Yeah, so it does, right? That's the thing you couldn't answer, but it does.
See.
And that's why, for example, I said I had to do this simplified icing one where I only think up and down. If I had done a magnet that can point any direction, you can do these calculations, but it's in a different universality class. So that number, there's an analog of that number, but it's a different number.
Thank you very much. Thank you. It's a really great talk.
Very well, thank you for coming.
Thank you so much. I think there's another person who just put their hand up.
Okay, I'm happy to stay on, but yeah, no one.
Yeah, I mean, as you said, people often leave through the questions, but that's normal. So
yeah, sure. You can stop. I mean, at some point, obviously, you can stop the video. I don't care, but I'm happy to stick around and chat. But anyway, yes. Sorry. Go ahead. Whoever it is.
I believe it's Tony. Maybe sometimes people accidentally raise their hands.
Okay.
Give them a second. Oh. Okay. Probably did it accidentally.
Well.
No, I'm here.
Oh.
Okay. Well, somebody go.
Yeah, it was a great talk. Thank you. I was just wondering where the 0.32 exponent came from.
It's either an experimental fact or there's a calculation you do. And now through actually in recent years, the calculational technology, the calculation, the renormalization group gives that to 3 or 4, 3 digits maybe of accuracy, more or less. So pretty good. Through some very fancy things. There's some new tricks that using this thing called conformal symmetry that gives that thing now better than that. But yeah, it's but yeah, you use the renormalization group to do these calculations, and you get that number. It's a great spectacular success of the theory. So you write down this field theory, effective field theory, and you can then compute order by order. And if you know what field theory Feynman diagrams, people have done up to actually, I think they've gone beyond 5 loops, 6 or 7 loops now. I forget how much they've done. So
does it correspond to anything of physical intuition, or it's just a number?
I mean, it's the formalism of quantum field theory, which goes by the name of Feynman diagrams. So I don't know what to say beyond that. Yeah, I gave some babble. It's understanding these interactions. It's doing quantum mechanics, but of fields, and it's a lot thing. And the tech. Yeah, in the seminar series, it would be good to get a Feynman diagram expert to come on and explain. There's been all this spectacular progress in recent years in understanding how to compute these things. Believe it or not, even though Feynman obviously is long gone, people are still learning how to do these things. So yeah, I'm not sure I have a pithier way of saying it than that. But well-established theoretical well-established theoretical tools. I'll let you compute that number.
Okay, thank you.
Thank you so much. I'm sure many of us are looking forward to that book you're writing, allegedly.
Yeah, well, there's you can look, a few things are on my webpage somewhere, but yeah, this talk was one, I thought maybe I would work on it more, but of course I didn't. Someone else was trying to talk. Did someone else have a question?
I was just going to say, like, in the meantime, do you have any other recommendations which might be manageable to second and third year undergrads to read? And I know you sent that.
Wilson's, yeah, the popular article. Well, obviously, that's a. I mean, Wilson's Nobel lecture is kind of curious. Sometimes it's too hard, but sometimes it's really nice. So you just look up Wilson's Nobel lecture. There's good books on the renormalization. So like if you look sometimes there's some books on StatMech, like if you look at the end, they have chapters. You probably, if you want just, you probably need to know some StatMech, have taken a decent StatMech class to get much deeper. But you can try, if you know a little bit of StatMech, you can probably try Wilson's Nobel lecture and then look at the end. So even if your class didn't do it, you can look at the end of various StatMech books. I always like, there's an old book by Pathry I always like. And there are books on the Renormalization Group too. So you can, of course, just try them, read the first chapter to one by John Carty, one by Nigel Goldenfeld are good. There's others as well. And maybe they're, offhand, I'm trying to remember how broad their introductory chapters are. But maybe they have good introductory chapters. I can't remember, but try that. Look randomly around. There's a review article, also a famous review article by Wilson and Kogut from the 70s. Kogut is the co-author. And again, the whole thing gets very technical, but maybe they wrote a good introduction, or you can, and then start with the more quantitative stuff. But yeah, it's hard to go from the Babel level at which I had to the non-Babel level that required to actually compute something.
Thank you. These recommendations are always really great, like hearing them from.
Yeah. So one thing I did in my book one chapter that is there, one of the few things that is kind of done thoroughly is I do try and explain pretty well what Landau theory is. And I think I tried to write it, if you at least know some basic StatMech, then hopefully you can follow that. And that really goes a long way to at least understanding the starting point of the RG. So what mean field theory is and things like that.
Mm-hmm. That's great. Well, we always lose a big majority of people over the questions, but if you've stayed so long, thank you so much. I want to give you all the opportunity to show your faces and say hi. So I'm going to stop the recording.